Okay, so in this set of slides, I'm going to introduce deep neural networks because as we discussed, when we work with Q functions or value functions or also policies, we might have a large state space, and then it's not going to be feasible for us to represent all those states by enumerating them in a table. So we're going to need some way of approximating functions with respect to these large state spaces and also large action spaces, and neural networks are going to be very useful for that. Okay, so this lecture, I'm going to introduce neural networks and some of the basics regarding deep learning. So some of you might already be familiar with this, so you can just sit back and relax, but I need to make sure that everybody is on the same page with respect to these notions. Okay, so as a quick recap, we talked about Markov decision processes, where one algorithm that we saw is very important is value iteration. And then the key is that in that algorithm, we have a value function, which you can think as a long vector that indicates what is the value of a policy with respect to each state. But I need to be able to enumerate all the states and represent that in a vector. Then we said, well, if we don't know what is the transition model, we can relax this and then simply work with the Q-learning algorithm. And then, for instance, it will use temporal differences to drive the learning. And now here we work with Q functions instead of value function, but it's the same problem, right? We're going to have now a table for every state action pair. We need to store a value for this. Okay, so those two algorithms, it's clear that their complexity now depends on the number of states and actions. So if I have lots of states and actions, or if I have even continuous states and actions, then these things are not practical. So concretely, if you consider the game of Go, right? So the game of Go has this board. There are intersections where I can put a stone. So any intersection can take 3 values. So either it's empty, or there's a white stone, or a black stone. Right? So then a rough estimate here is that you could have up to 3 to the 361 states. So that's very large. If we consider in robotics a very simple control problem, we talked about the inverted pendulum problem, where you've got a cart, there's a pole, and then the pole might fall due to gravity, and the problem is just to keep it balanced. Right, so in this problem, a natural description of the states would be a combination of position, velocity, angle, and angular velocity. But the problem is that this is a continuous state space, so we really have, I guess, a continuum of states, and we can't enumerate that. As a last example, so in recent years, game playing has been very important, at least for benchmarking various reinforcement learning techniques. So here I'm showing you some screenshots of different Atari games. And then the idea is that in the same way that humans can play those games, today we can get or we can design some reinforcement learning agents that will simply take as input a screenshot. In fact, all the images as the agent plays the game, and then will directly control, I guess, whatever can be controlled in the game. So in this case, these are cars, and here I'm not sure, but in any case, yeah. in each game, there's something that can be controlled, right? And then so the agent will simply control these things. Okay, so in terms of the state space, so here the state can be defined by looking at essentially the entire history of all screenshots that have been seen in the game. And then if we just look at one screenshot, which is one image, right, how many possible images could there be? Right, so it would be the number of pixels raised to the power of the number of values for each pixel. And in reality, pixels, you can think of them as also being continuous. So this is an extremely large state space. Right, so we can't enumerate states in these problems. So we need a way then to represent functions that depends on states and actions that will be able to deal with this. Okay, so yeah, so I guess the functions that matter for us are the policy, because it depends on the state, the Q function depends on states and actions, and the value function. So all of those three policies, if we want to deal with the type of problems that I just mentioned, we need to approximate them. We can't use tables or vectors for them. So let's focus for the rest of this lecture just on the Q function, but then in future lectures we're also going to see how we can approximate the policy and the value function, but at least this will give us some intuitions about what we can do, and we'll generalize that to the other functions afterwards. Okay, so the Q function normally depends on state and action pairs, and let's say here that a state is defined by a set of features. Okay, so for instance, if I just go back, in the case of the inverted pendulum, you see a state is defined by a set of features that corresponds to position, velocity, angle, angular velocity. Right? In the case of Atari games, if we restrict the state to a sequence of past images, then you could think that there is one feature per pixel that indicates the value of that pixel. So it would be a really long vector, but it's a vector of features as well. Okay, so we're going to go ahead with this idea that states are defined by a vector of features. And now we'd like to define a function from states and actions to real numbers. And maybe the simplest is just to consider a linear approximation. Right? So here, these features would all correspond to numbers. And then perhaps we can just take a weighted combination of that and then say that, okay, hopefully there exists some linear approximation that can represent the Q function. Now, linear is obviously going to be restrictive, so we will want to also consider nonlinear approximations. And what is very popular these days is to consider neural networks because they are a universal function approximator. So here, I'm going to represent my neural network by a function g. This neural network will have some inputs as well that correspond to our features, and then it will be parameterized by some weights. And then we're going to see in a moment how this is defined, but roughly speaking, it's again just a function with inputs and some weights, and then it produces a number that we can interpret as the Q value. Okay? All right, so now what exactly is a neural network? So a neural network is obviously something inspired by, I guess, the human brain and well, I guess brains of different animals as well in general, where we're going to have a network of units. These are going to be really computational neurons, and then they're going to be linked by some weighted edges. So I've got a graph here where every node is a computational unit, and then I've got some edges between them. What I'm not showing in this picture is that each edge is going to have a weight, and then we're going to see in a moment how we can do computation with that. Okay, so each node is a unit, and then we're going to characterize these units by the following information. So each unit, like if I take this node right here, it receives some information from the previous layer. So this information is going to be characterized by a vector of numbers I'm going to call the inputs. And then those inputs, I'm going to multiply them by some weights. The idea is that the inputs that come from the previous layer are going to be weighted by whatever are the weights on each edge. And then, so I'll take a linear combination. I'm going to add to this another number that I'm going to call the bias. The bias is essentially just to allow us to shift this linear combination either up or down. And then finally, I'm going to compute some function h that is known as the activation function. And generally speaking, is going to be a nonlinear function. So to summarize, every node in here is a computational unit. And traditionally, what each of those units does is take a linear combination of the inputs that are feeding to that unit, and then take a nonlinear transformation h that is known as the activation function, and then it produces an output. Okay, any questions regarding this? Okay, very good. Now, to be more precise, right, so here I've got a simple neural network where I can write down all the information. So here I've got an input layer. I'm going to denote my two inputs by x1 and x2. Every edge here has some weight. And then I also have a bias, B, that is fed into each unit. And then for the final layer, I also have some edges with some weights, and then there's also a bias that feeds in. Okay? And now we can see that the hidden units that are here are going to be computing the following function. So I'll take a linear combination of x1 and x2. This is what this means. So I take a linear combination of x1 and x2 plus the bias, which corresponds to this edge here. And then I apply the activation function, h1. We're going to see in a moment what are some of those possible activation functions. But for now, it's just going to be a function that's going to transform, generally speaking, in a nonlinear fashion, this linear combination. And then this will produce the output, zi or zj. So this will produce the output that goes along each edge here. The output unit is going to do something similar. So it takes a linear combination of those hidden units plus the bias, and then we apply an activation function, h2. So here this just denotes the fact that it might be different from the activation function for the previous layer. Right? So each unit can have a different activation function, and then it produces an output yk. Now when I put this together, what is really a neural network? It is a mathematical function that is composed by sub-functions that each correspond to the computational units. So here you see I will first do the computation that corresponds to the hidden units, and then this feeds into the output unit that does its computation right here. Right? So this feeds into the output unit, and then I get yk. So in general, any neural network, there is a corresponding mathematical function that represents what the graph is really computing. Okay, so in terms of activation function, there's lots of possibilities. Traditionally, these were some of the common activation functions. So you could have a thresholding function that just returns 1 or minus 1, depending on whether the unit has a value a that would be positive or negative. You could also have a sigmoid function. Let me just draw what a sigmoid function looks like. So the sigmoid function would start near 0, gradually increase, and asymptotically reach 1. And then it crosses at 0.5. Okay, so the sigmoid function is essentially some sort of squashing function because it takes any input and then it will output something that is between 0 and 1. So that's the mathematical form of that function, and it's very useful to produce a probability because then the output is between 0 and 1. Here's another type of unit, the Gaussian unit. This one essentially is named after the Gaussian distribution because the mathematical form is effectively the same as the one that defines the Gaussian distribution. So it's an activation function that has a shape similar to the Gaussian. So in this case, right, then it would correspond to a little bump like that. Okay, so a nice bell shape, and that's another popular one. The hyperbolic tangent function is yet another one. It is closely related to the sigmoid. So in this case, so it would start around -1 and go up to roughly +1. Okay, so it's also a squashing function. The main difference is that it goes from -1 to +1. Okay, and then the last one, the identity, is simply a function that indicates that we're not changing what is being produced by that unit. So it's a way of saying that we don't have any activation function, right? That nothing is really being computed. So historically, these were some of the popular ones. Today we have a lot more, but you'll see those in the literature very frequently. Okay, so neural networks became quite popular for several reasons, but in particular, there was one theorem at some point where it was shown that neural networks with at least one hidden layer of sufficiently many sigmoid, hyperbolic tangent, or Gaussian units can approximate any function arbitrarily closely. Okay, so the idea is that in machine learning, we often need to approximate some functions. Like in the case of reinforcement learning, there's a Q function that might be a complex function over a continuous space. And now we'd like to represent it, and we don't want to be stuck with, like, let's say, just linear functions or just quadratic functions. We'd like to be able to approximate any possible function. Well, it turns out that a neural network that has at least one hidden layer and then uses sigmoid, tanh, or Gaussian, right, can approximate arbitrarily closely any function. So this is beautiful because at some level it suggests that perhaps all we need are neural networks. I mean, in reality, there's all kinds of other issues, so neural networks are not the answer to everything, but they are quite powerful. Okay, so let me draw a picture as well to illustrate why this theorem holds. So this will be more, I guess, an intuition as opposed to a proof. Okay. So let's say that we have some arbitrary function that we're trying to approximate. What I can do is then construct a neural network. My neural network will simply have the identity function here. And let's say that I've got a certain number of children. Let's say k children, so I'll have weights 1 over k for each one of them. Okay. And then here, let me use the Gaussian units. Okay, so these are all Gaussian units. So what I'm effectively defining here is a mixture of Gaussians. Okay, and we saw earlier that Gaussians have this nice bell shape. And there's a parameter that allows us to vary the width of the Gaussian, which is typically the variance parameter, right? So it tells us how wide this bell shape is going to be. Now, if I want to, what I could do here is have a very large number of Gaussians. Each one of them could be very slim, and then I could tile them in a way where it will roughly approximate my curve in this fashion. Okay, so then I can get something that is arbitrarily close by just tiling together lots of Gaussians that are arbitrarily thin and arbitrarily close to each other. So if I have enough of them, then I can approximate my curve arbitrarily closely. Okay? And so this is with a Gaussian unit, but there's some similar proofs, or at least similar constructions, that are possible with the sigmoid and the hyperbolic tangent as well. Okay, any questions regarding this? Yes?
Is the mean of the Gaussian also a parameter?
Yes, so if we go back, so here you see the Gaussian would have a parameter mu that corresponds to the mean, and then sigma for the width. So that's why here I can simply choose the mean to correspond to different locations, and I can choose sigma to be very small. Okay, so now we've seen neural networks, and an interesting question now is going to be, how can we optimize the parameters of the neural network? Right? So if you recall, the parameters of the neural network are the weights. So if I just go back, oops, let's go back. Right here, so you see in the network, all the edges have some weights, and these are the parameters that can be adjusted. Okay? So to adjust those parameters, we need an algorithm to train the weights. And then a simple approach is going to be to define an error function. So for instance, I might have a target y. So I might, let's say that I'm trying to do regression where I'm trying to predict some value, and I happen to know what is the target that I need to produce as an output. So this would be y. And then I can compare that to what my neural network produces as an output. And here again, f is the mathematical function that corresponds to the neural network. It takes as input x, and it has parameters w. Okay? So now, if I want to train my neural network to approximate some function where I happen to know what are the inputs and what is the target, then I can simply try to minimize some distance between the two, and a common distance would be the Euclidean norm. So here, I would simply take a sum of all these errors with respect to all of my data points. So here, n is simply indicating all the data points. And then, so this would be my error function, and I will try to minimize that. Okay, so to minimize this is an optimization problem. In general, it's going to be non-convex. It's going to be a very difficult optimization problem. So for most neural networks, we don't have closed form solutions. We don't have guarantees for finding the global optimum. But in practice, what we can do, which can still be quite effective, is simply to apply gradient descent. Okay? And here, just to illustrate, so let's say I've got some function. Actually, no, let me redraw this. Okay, so let's say this is my function that corresponds to the error function. Okay, so now I'd like to adjust the weights w to find the minimum of this function. So here, on the x-axis, I've got the weights, and then on the y-axis, this is E of w. Right? So I've got an optimization problem, and ideally, I want to find the smallest error possible. So I want to find this point here. And then, so again, it's an optimization problem. And gradient descent, what it does is simply that we start, let's say, at some location, and then we're going to measure the direction of steepest descent. This is what the gradient gives us. So it would be this direction, and therefore we would make a step in this direction, perhaps arrive at this new point, measure again what would be the direction of steepest descent, make another step, arrive here, and so on, and then eventually we converge to a local optimum. And this particular picture just so happens that I converge to the global optimum, but you can appreciate the fact that if I started here, I would perhaps converge here, and if I start here, I would converge here, right? So gradient descent is just this very simple technique where you can improve until you arrive at a local optimum. Okay, so a lot of techniques for optimizing neural networks are based on that. And in fact, if you use a package like TensorFlow, PyTorch, Theano, and many others, what they all have in common is automatic differentiation, which means that you have your neural network, it's a mathematical function, and then you specify an objective like Euclidean loss, and then it will automatically compute for you the gradient. Okay, so then you can define a simple algorithm that will take a step in the direction of the gradient, where here eta is the step size. Okay, so this was for basic neural networks. Now let's talk about deep neural networks. The main difference between a regular neural network and a deep neural network is just how many hidden layers we have. Okay, so traditional neural networks would typically have one hidden layer, and that was in part because of this theorem where I showed you earlier that as long as you have at least one hidden layer, you can approximate arbitrarily closely any function, and therefore traditionally most of the neural networks were restricted to just a single hidden layer. And yeah, we knew that in theory this was going to be sufficient, but in practice it doesn't mean that having several hidden layers there's no advantage. In fact, having multiple hidden layers allows us to represent things more compactly and to have networks that are more expressive. At least more expressive with respect to the size of the representation. Okay, so yeah, so that's the main advantage, and then so that's why in recent years there's been a lot of enthusiasm with respect to deep neural networks, because then these would have multiple hidden layers. But then the challenges now are how do we train those deep neural networks effectively, and in particular also how do we avoid overfitting. So that first one, how do we train deep neural networks effectively? You could say, well, why don't we just apply gradient descent? And yes, in theory, you can just apply gradient descent. But what happens, I'll get to this in a few slides, is that then there's an important problem known as the gradient vanishing problem. And so in theory, yes, we can use just simple gradient descent. But then if you have gradients that vanish, gradients that become arbitrarily small, then you're not making much change to your network. And as a result, it becomes very difficult to train these neural networks. Okay, so yeah, before I get on with this, let's come back to the question of expressivity. So here we can compare a deep neural network. Let's say in the context of Gaussians, we could obtain a hierarchical mixture of Gaussians. And then if we have a shallow neural network that just has one hidden layer, we can obtain a flat mixture of Gaussians. So what I drew here on the board would be essentially a shallow neural network, because here the idea is that I have Gaussians that would be connected to the inputs. Okay, and then I have a single hidden layer. So this is the hidden layer, and then the output is here. Okay, so this is an example of a shallow neural network. But now we can consider a hierarchical or a deep neural network. Okay, so I'll have the Gaussians again that are connected to the inputs. And next, what I can do is, for instance, take some sums. Let me add one more Gaussian here, and then here's another sum. Okay, and then after this, I could take some products. In fact, actually, I don't need this. Let me remove this. I'll just need those two. Let me define some products. Like this, and then some sums. Like this, and so on. So if I build a hierarchy where I alternate between sums and products, okay, what's going to happen is that if I can always flatten this hierarchy, but when I flatten it, I will get exponentially many Gaussians. And this implicitly corresponds to taking an exponentially large mixture of Gaussians. So in fact, this type of neural network is also known as a sum product network, where the nodes are sums and products, and then you just alternate between the sums and the products. And then when you do this alternation, the idea is that the sums corresponds to taking mixtures, just like what I did here. And then the products are essentially just going to be multiplying together two distributions. And then when I simply flatten this by using, by distributing the operations, what happens is that you see here this sum just has a mixture of two Gaussians, and this one as well. But now when I multiply these two together, right, so I'm multiplying a sum by another sum, so together, right, so this would correspond now to 4 Gaussians. And so it would always be quadratic in terms of the number of Gaussians in each mixture. But if I continue and I have higher and higher levels of sums and products, then I can build a hierarchy that will essentially correspond to an exponentially large mixture while just keeping the size of the hierarchy linear. So this is where there's a nice advantage because deep neural networks can then represent more compactly what would be otherwise, what might take otherwise exponential size when you flatten the structure. Okay, so this is in theory, but now in practice, you might say, well, give me an example, where depth matters. And it's worth looking at an important challenge that essentially sparked a lot of interest in deep learning. And this was the ImageNet Large-Scale Visual Recognition Challenge. So in this challenge, the problem was that we were given lots of images, millions of images, corresponding to thousands of categories. And then the computer has to learn to recognize these different categories of objects in all those images. And so here I've got a chart that shows some of the best approaches year by year. And then back in 2010, for this challenge, the classification error was still 28%, so it was quite high. And then there was a drop that was quite significant in 2012 to 16%, and this is when the community started using deep neural networks. So yeah, so here, up until 2011, the state of the art was to use handcrafted features with support vector machines, and then starting in 2012, deep convolutional neural networks were used. Now, the accuracy kept on improving, and what's interesting is that if you look at the depth of those neural networks, so the one in 2012 had 5 layers, then in 2013, 8 layers, and it kept on increasing, and then also the results kept on getting better. Now, the depth is not the only reason for those results to improve, but it was considered to be an important factor, and definitely still today the depth matters, and in any case this was strong support for the argument that depth is important. Okay, so now let's come back to how do we optimize these neural networks. So we saw that we can just use gradient descent, but then there's a problem when you have a neural network that has multiple layers. So here I've got a graphical representation of a neural network that has 4 layers. Let's say these are the outputs. And then when I do gradient descent, what will happen typically is that I will have some gradients that have a reasonable size near the output. But then if I go back into the network closer to the inputs, then the magnitude of the gradient gets smaller and smaller. Okay, so here you'll notice that I have edges that are thicker to simply indicate that the gradient associated with the weights on those edges is going to be of a reasonable magnitude. And then when it gets thinner and thinner, it simply means that the magnitude of those weights is getting smaller and smaller. Okay, so this illustrates the gradient vanishing problem because when you do gradient descent and you compute the gradient by automatic differentiation or any other approach, then what will naturally happen is that the weights here at the beginning of the network will barely be updated because the gradients are going to be close to zero. Okay, so when you do gradient descent, the idea is that you have your estimate, you take a step in the direction of the gradient, and then the simplest idea is just to take the magnitude of the gradient as the size of the step. So if your gradient is small, then you take a small step. And if your gradient is almost zero, then your estimate barely changes. And this is not good because if you initialize everything randomly, then it means that at the beginning, you're feeding your inputs into a part of the network that barely gets updated, has random weights, and then you can question how can the rest of the network compute anything useful because the beginning is just computing random stuff. Right? So then it would not produce good results. So we need an approach that will update everything, and especially the first part of the network. Okay, so this problem occurs in large part because some of the units that were popular at the time were sigmoid and hyperbolic tangent units. And if you recall, those units correspond to functions of this shape, right? So the sigmoid function goes from 0 up to 1, and the hyperbolic function goes from -1 up to 1. Okay, so these are both squashing functions. And now, when we look at the gradient of those functions, there's something really interesting where the gradient, so that would be the slope is the steepest at the y-axis when we cross the y-axis, and it's still smaller than 1. Okay, so the slope is going to be smaller than 1 in both cases. So here the problem is that when you compute gradients, if you have in your computation some numbers that are smaller than 1 and you multiply them together, you get numbers that get smaller and smaller and smaller. And indeed, what happens is that the gradient vanishing problem can at least be explained intuitively by this idea that we're computing some numbers that are going to be smaller than 1. You multiply them together, they get smaller and smaller, and at some point they converge to 0. Okay, and it has to do with the fact that the sigmoid and the hyperbolic tangent functions both have gradients that are smaller than 1. And also if you look at the functions themselves, right, so the sigmoid function always produces an output that is between 0 and 1. And then the hyperbolic, it's between -1 and +1. But again, if you multiply numbers that in magnitude are always less than 1, then you get numbers that get smaller and smaller. Okay, so here I've got a simple example to illustrate what happens when I have a neural network that just has a chain, and then the input gets multiplied by a weight, then I apply some function that could be either the sigmoid or the hyperbolic tangent. So in this case, I'm just going to go with the sigmoid. So let's assume that this is the sigmoid that is applied. Then I multiply by W2, I apply the sigmoid again, multiply by W3, sigmoid, and so on. Okay? So very simple neural network. Now, if you do the math and you compute analytically what are the gradients with respect to each one of those weights, then you would arrive at the following expressions. Okay? So here I'm sparing you the details of how this is obtained. In practice, again, you would use automatic differentiation. But now, if we have these formulas and we analyze them, you'll notice that the gradient for the fourth weight, so this is the one close to the output, it has an expression, right, where I'm multiplying the gradient of a sigmoid times the output of a sigmoid. These are two numbers that are smaller than 1. Therefore, I'm going to get something that is also smaller than 1. But now if we look at the third weight, so we're going back, we're looking at the third weight, this one will have an expression that has, again, same beginning, right? So derivative of a sigmoid times a weight times another derivative of a sigmoid times another sigmoid. And roughly speaking, right, so we have the first two terms that are exactly the same. We can think, roughly speaking, that the last term is also the same. And what we've introduced are those two terms in the middle. And then so this term is smaller than 1. And now this weight W4 could be anything. But traditionally, people initialize their weights also to be numbers between -1 and +1. So again, numbers that are small in general. So here you multiply effectively 4 numbers where 3 of them are necessarily smaller than 1. And then this weight is typically initialized to be between -1 and +1. So therefore is also going to be small. So this is often going to be smaller than the gradient for the fourth weight. If we continue, so for the second weight, we just get a longer expression, and it's the same idea. We're just going to multiply lots of numbers that are all between -1 and +1, unless the weights actually do grow over time. But if they remain in that interval, then it's all between -1 and +1. So this will be smaller than the previous one. And then same thing for W1. So as you can see, those numbers tend to get smaller and smaller over time. Okay, so this is an example to illustrate the gradient vanishing problem. Obviously here I took a very simple neural network, and it might not be the best neural network, but in any case, this generalizes in practice to larger neural networks. Any questions regarding this? Okay, let's continue. All right, so now that we've talked about this gradient vanishing problem, there are several solutions that have been discovered over time. They include to do some pre-training. We can use a different type of units that are known as rectified linear units. We can also use batch normalization, and then we can also architect our network differently by using skip connections. So I'm not going to have time to talk about all of this, but let's at least introduce rectified linear units, because when you work with neural networks today, most of the activation functions, in fact, are chosen to be rectified linear units as opposed to the sigmoid or hyperbolic tangent. Okay, so what is a rectified linear unit? It's going to be a function that is 0 here and then linear afterwards. Okay, so the function is defined to be the max of 0 and a. So it is a nonlinear function because of the max operator, but otherwise it's a piecewise linear function because there's a piece that is 0 and then there's another piece that is linear. Okay, so initially, when researchers started working with rectified linear units, they were not seen as very attractive because this was a function that is not smooth, right? So it's a non-smooth function, and if you want to compute the gradient, so at 0, the gradient is not well defined because it's not smooth. So those rectified linear units were not popular for a long time. But then in 2012, if I just go back, the solution that was proposed here for AlexNet did start using those rectified linear units, and it was viewed as an important component because then it allowed to mitigate to a large extent the gradient vanishing problem. And so now the question is, why is it that with these types of units, the gradient would not vanish? And it turns out that if we look at the shape of the function, because here it's 0, and then after that it's linear, the gradient of this is either going to be 0 or 1. Okay, so the gradient by default is 0 or 1, because if we're in the 0 part, the gradient is 0. And if we're in the linear part, the gradient is 1. Okay, and this, it's not clear that this is necessarily a good idea, but the reality is that whenever it's 0, it's the same as saying that whatever came to that unit before that doesn't matter. And at that point, you could say the gradient has completely vanished, and that's really bad. But when it's in the A part, then the gradient is 1, and nothing has vanished. So here, what happens is that as long as you've got some paths in your network where all those rectified linear units are in the A part, so the linear part, then you'll have a gradient that is 1, that is not vanishing. And then you'll be able to update everything all the way back to the inputs as long as you've got some paths that are all with the linear part. So with this, then we can propagate gradients, and then convergence is much faster. Now, it might be tempting to say, well, since the main issue otherwise with this type of unit is that it's not smooth, so here you see it changes abruptly, maybe we can make that smooth by using an approximation. And then so a common approximation, or a soft version of that, is known as the soft plus, and it has the following formula. So the soft plus is illustrated here, and then you can make it arbitrarily close to the rectified linear unit simply by changing the base of the exponent, I believe. Yeah, that's right. So if we change the base, then we can make that arbitrarily close. The problem is that if you look at this function, right, so the slope of this function starts to be close to 0. It gradually increases. But when it increases, it never becomes completely linear, so it will always have a slope that is less than 1, and as a result, we're still going to have the gradient vanishing problem. Okay, so the soft plus looks like a good idea, but it's not. Okay, it actually does not solve it does not mitigate the gradient vanishing problem. So you really want to use the rectified linear units, and then the fact that it's not smooth is not a big deal because we can use subgradient techniques to do the optimization.